Okay, let's take a look at some problems that can utilize what we just learned about the points on the unit circle. Here's some problems directly out of the textbook. So we have this problem number 15 here, and it says in these problems, problems 11 through 16, the point P on the unit circle, that's important, this point is on the unit circle, that corresponds to a real number t is given. Find sine t, cosine t, tangent t, and so on. So t is the angle. And what they're telling us is in number 15 that these are the coordinates of a point that is on the unit circle. So right here, this radical 5/3 and 2/3, that's that obviously then is the cosine and the sine of some particular angle. And so they want us to find all the trig function values for this particular angle whose point that would be on the unit circle that is on the terminal side of the angle is these two coordinates. So again, since this is a point on the unit circle, then this must be the cosine and this must be the sine. And so for number 15 here, right, let's just write out the 6 trig functions for sine t. T is what they're calling the angle here, sine t, cosine t. And then we've got tangent t, of course, cosecant t, secant t, and cotangent t. So the sine and cosine we already know, right? The cosine is radical 5/3. And then the sine of t is 2/3, which means that the reciprocal functions over here across from them would just be the reciprocals of that. So this would be 3/2 for the cosecant. And then 3 over radical 5 for the secant, which is, when we rationalize that, it would be, what, 3 radical 5/5. The tangent now, a couple ways you can come up with that. One is you can think about the fundamental identities that the sine of some angle is the sine over the cosine of the same angle is the tangent. So you could take the sine here and divide it by the cosine. That would be one way to do it and get your tangent. And then to get the cotangent, you could take cosine divided by sine and then simplify that. It ends up being, one fraction divided by another, which in case you'd have to invert and multiply those to simplify. But another way to think about it is, since the sine, they give you the sine, that's opposite side across from the angle over the hypotenuse. And then the cosine is going to be the adjacent side over the hypotenuse, which means you actually have all 3 sides of a right triangle that would resemble the situation here, the angle. So let's call this down here theta. And so our hypotenuse is 3. We can see from the sine and the cosine. The side opposite that would be 2, opposite the angle theta here would be 2, and adjacent is radical 5. So you could just draw up a triangle then, and then come up with the tangent there would be 2 over radical 5. And you rationalize that, it's going to be, what, 2 radical 5/5? Okay, and then reciprocate that before, look at what we had for the tangent. Before we rationalize it, it was 2 over radical 5. So to get the cotangent, we could just reciprocate that, which would be radical 5/2. So these are our 6 trig functions for this angle t. And the key here was that this point was on the unit circle, so automatically we knew that they were actually giving us the cosine and the sine of this angle t. Now the second problem here, this number 19, is a little different. It is the point on a circle, but we don't really know that it's the unit circle. We just know that it's a circle. It says the point P is a circle on x squared plus y squared equals r squared. That is also on the terminal side of some angle theta. And then we're supposed to find the six trig functions for this angle theta. So they said we have a point, and that point is on the terminal side of the angle theta, and we're supposed to come up with the six trig functions for that if they give us this point here, negative 2, 3. Now, it's not the unit circle, so we cannot say that negative 2 is the cosine or 3 is the sine. But let's go ahead and just talk real quickly about something that you should remember from a college algebra course, and that is that the standard form for a circle, x minus h squared plus y minus k squared is equal to r squared. That is the standard form for a circle where hk is the center point and r is the radius. Okay, so now in this case, they gave us the equation was x squared plus y squared equals r squared. Now, how do you get to x squared plus y squared equals r squared from this standard form? Well, h and k must be 0 in this situation right here, which means this actually is a circle. X squared plus y squared equals r squared is a circle centered at the origin, because the center is 0, 0 if there's nothing subtracted or added to the within the x squared or within the squared terms there. So let's go ahead and just do a simple quick sketch here. See, where was that point? The point was negative 2, 3. Let's see if I can straighten that up. Okay. So we're going to go left 2, up 3. 1, 2, 3. So this is the point that is on, it says it's on the edge of a circle that is centered at the origin. So somehow this circle goes around something like that. It's the best I can do. There's the point negative 2, 3. And so our angle, remember the terminal side of the angle is what goes through this point, they said. There's the terminal side, here's the initial side. So here's our angle theta that we're trying to find all the trig function values for. We've seen a similar situation to this before in a previous class meeting. And that is, if we drop a perpendicular down from this point on the circle, go straight down to the nearest x-axis, and then come back over to the origin. Now we have a right angle here, and then we have what we were calling is a reference angle. That's the reference angle for theta. And from that reference angle for theta, we learned that we can come up with all of the trig function values for theta using the reference angle. I also mentioned in class that, knowing these points here also indicate to us what we can use for the sides of the triangle. Now, some may disagree with this, but I'm going to go ahead and do this. I'm going to say, well, we went to the left 2 units to get over here. It's left 2, up 3. So I'm actually going to show that side of the triangle as being negative 2, even though we don't use negative lengths. But if I allow it to be negative, then I'll come up with all the proper trig function values for theta. Okay. So, and then this height here would be 3. So knowing all that, if I use the Pythagorean theorem, then this would be what, 9 plus 4, because remember a squared plus b squared equals c squared, where c is the hypotenuse. So this would be 9 plus 4 is 13. So it would be square root of 13 would be the hypotenuse here, square root of 13. So now using that, you can come up with all 6 trig functions of theta. So we've got sine, cosine, and tangent, right? And the sine of this would be what, 3 over radical 13? which, and when we rationalize it, would be 3 radical 13 over 13. And then the cosine would be negative 2 over radical 13. And then rationalize that, it would be negative 2 radical 13 over 13. And then the tangent would be a 3 over negative 2. And so these are the exact values for those first 3 trig functions for this angle theta. Now remember, we're actually using this reference angle alpha to come up with that. And if I allow for these negative lengths here when I needed to, like if I'm going to the left of the x-axis on the x-axis, and then I'm going to make that a negative 2. If I do that, it helps me get the signs correctly. Otherwise, I just have to remember, since this angle lies in the second quadrant, then the only trig functions that are positive there are sine and its reciprocal cosecant, and all others are negative type of thing. So I have to remember all that stuff, which is fine, but I think this is a quicker way to do it. All right, so let's do the last 3. So we got cosecant theta, secant theta, and cotangent theta. So the reciprocal here of the sine before I rationalized it, so it will end up being radical 13 over 3. And then the reciprocal of the cosine, if before I rationalized it here, will be a negative radical 13 over 2. And then lastly, negative 2/3. So those are some good couple of examples that help us. Well, the first one definitely utilized the unit circle, this number 15, and then this number 19 down here. This actually was kind of a little bit of a trick, because, or kind of almost a trick problem, because we might think that it's the unit circle, but it's not. We can't assume that. And the radius, in fact, here was not 1, it was radical 13. So, okay, hopefully that helps you understand a little bit using the unit circle, as well as kind of this problem number 19 was a little bit of a review.